In this video, we're going to look at geometric series. We're going to look at how we can actually find a way to figure out exactly what this particular type of series sums to. So to start off, let's define what we mean by a geometric series. A geometric series has the following form. It is the sum of some constant, which often we'll just assume the constant is 1, but there will be cases where we don't, of 1 plus r squared plus r cubed, and so on. And it goes on forever. And we can write this using sigma notation as the sum of a constant times r to the k, where k goes from 0 all the way on up to infinity. And we start with 0 because r to the 0 is 1, and that includes this constant term with no r's in it. Okay, so that's called a geometric series. And notice here we can think of that as summing the terms of a sequence where the terms in the sequence that we're adding are just a constant times r raised to a power. Okay, some interesting properties of this geometric sequence that we've touched on earlier, but I'll remind you. So geometric sequence has terms that are just some constant times r to the k. And the main thing to notice is that if you take two consecutive terms and you take their ratio, you will get cr to the k plus 1 over cr to the k. The ratio, notice the c's cancel. Most of the powers of r cancel, and we're left with just r. So there is a constant ratio between consecutive terms. Okay, so let's look at an example where you might want to use a geometric series. In fact, we'll look at 3 different examples of sort of real-world scenarios where geometric series might arise. The first example is thinking about, well, the coronavirus outbreak that we're dealing with at the moment. So suppose 64 people are infected on day 1, or on day 0 rather. And let's suppose that each day there are 25% more infections, new infections that is, than the previous day. We can describe the total number of infections we're using a geometric series. All right, and what's the ratio here? Well, the initial number of infections was 64. The next day, we're going to have 25% more, so 64 times 1.25, or 5/4. The next day, we'll have 64 times 5/4 squared, which is just 5/4 times what we had in the previous day. And in general, on the nth day, the number of new cases would be 64 times 5/4 to the n. And so if we want the total number of cases, well, we could compute partial sums. The total number of cases on day n is just going to be a0 plus a1 all the way on up to an. And we could write that as 64 plus 64 times 5/4 plus 64 times 5/4 squared, all the way on up to 64 times 5/4 to the n. And notice, actually, that's a partial sum with n plus 1 terms since we started with 0. So I'm going to stop at 1. So this is now going to be a partial sum with n terms. All right, so the nth partial sum has n terms. And notice we can write that as 64 times 1 plus 5/4 plus 5/4 squared, and so on, up to 5/4 to the n minus 1. And so the ratio, the r from the geometric series is 5/4. Each day is 5/4 the previous one, and the constant is just 64 here. Okay, and if we wanted to find the total number of cases, the sum, S, would be the sum from n equals 0 to infinity of 64 times 5/4 to the n. And as you might guess, since each day we have more cases than the previous day, this is probably going to be a divergent series. In fact, if you look at the nth term test, an was 64 times 5/4 to the n. As n goes to infinity, what does that approach? Well, multiplying 5/4 by itself over and over again makes this bigger and bigger and bigger. And so an goes to infinity. And what we said last time is that the only way that a series can converge is if the terms approach 0. And this not only does it not approach 0, but they're actually growing. So by the nth term test, the sum must diverge, since an does not go to 0. So that's bad news, unfortunately. If this pattern of growing by 25% each day were to continue forever, then the number of cases would be infinite. Now, the good news is that can't possibly happen. You can't grow at a rate of 25% indefinitely. At some point, that growth is going to have to slow down. Okay, so there's a geometric series. When we're multiplying by some constant factor each step, then we're going to see this sort of geometric series behavior emerge. Let's look at another example. Let's suppose a ball is dropped from a height of h. Okay, it hits the ground, and then let's suppose that it bounces, and maybe we'll call that h0. Let's suppose it bounces so that the next height is exactly 3/4 of the previous height. And so that continues, so it goes up, and then it goes back down, and then the next bounce will be 3/4 of that. And so we would say that h2 is 3/4 of h1, and that this continues indefinitely. All right, so hopefully you have the picture. We drop the ball, it bounces, it bounces, it bounces, it keeps bouncing, but every time it bounces, the height of the next bounce is 3/4 of the previous one. And the question is, how far does the ball travel? All right, let's suppose that the initial height is 1, and so the next bounce is going to be 0.75. The one after that will be 0.75 times 0.75, and so on. All right, so let's see if we can describe this. Let's let S be the total distance traveled. And you notice from the first drop, we're going to travel 1 unit, right? If we drop from a height of 1 meter, we'll travel 1 meter. And then let's just think about the downward part in a moment. Forget about bouncing back up. But if you drop 1 meter on the first drop, the next time you drop, you're going to drop a total of 3/4 of that. And then the next one after that would be 3/4 of that. So 3/4 times 3/4. And you could see that if we're adding up all of the bounces, we're just going to get 3/4 cubed and so on. And it's going to continue forever. And so this is just the downward part. And then if we want to think about how far you travel when you're bouncing back up, well, for the first bounce, we didn't actually go up at all. We just went down. But for the second one, we had to bounce up exactly to the same height that we dropped. So we'll have 3/4. And then for all the subsequent bounces, we'll bounce up the exact same amount that we fall down. Okay, so the total distance traveled can be written as actually involves two infinite sums. Notice the first one is the sum of 3/4, and we want to include all of the powers we include 3/4 to the 0 on up to infinity. And then the second one, we don't actually include 0, we start with 3/4 raised to the first power. And so we could write that as the sum from 1 to infinity of 3/4 to the n. All right, so this means that the total distance that the ball has traveled, can be written as the sum of two different geometric series, one that starts with 0 and one that starts with 1. And here the constant term is 1, and the ratio of consecutive terms is 3/4. All right, now in this case, if we were to apply the nth term test, the things that we're adding up look like 3/4 to the n. And notice that as n goes to infinity, well, if you multiply 3/4 by itself an infinite number of times, every time you multiply by 3/4, it gets smaller. So we would say that an goes to 0. And so this sum might converge. It's not clear. We're not sure if it's going to converge. The nth term test does not tell us that it diverges, but it doesn't tell us that it converges either. So this differs from the last problem, and the reason is that the r was less than 1 here. And so what we're going to find in one of the next videos is that there's a critical point in terms of the values of r. If r is small, we could potentially have a convergent sum, but if r is too big, then it's going to be a divergent sum, and we'll make that precise later on. All right, so there's a second example where a geometric series arises. We will come back to this problem and actually figure out whether it does indeed converge and what it converges to if it does, and again in the next video. All right, so one more example. Suppose Bob gets $1,000 and he spends $90% and saves 10%. Okay, and let's suppose that when he spends it, all of those people that receive the money that he spends do the same thing. And so everyone else is going to spend the money they receive. So everyone's going to spend 90% of what they receive. And save 10%. The question is, how much total spending is caused by the original $1,000. Okay, so the idea is Bob gets $1,000, he spends $900, he saves $100. Then the person who received that $900 spends 90% of it and saves 10% of it. And then the person who received that 90% of 90% does the same thing. And so that pattern continues indefinitely. And so let's see if we can write down a nice little sum to represent that. So Bob is going to spend $1,000 times 0.9, right? He spends 90% of what he gets. And then that money goes out, it's given to someone else, and so that person who receives that money is going to spend 90% of that, which is the same thing as multiplying that quantity by 0.9. And so we could simplify that by writing it as 0.9 squared. And so now this is the money that was spent. And so the next generation of people who receive it are going to spend 90% of that. And the pattern is going to continue. So we're going to keep spending 90% of what we receive. And so this idea that when somebody receives money, there's sort of this trickle-down effect is an important idea in economics, that there are repercussions to adding money to the economy. They go far beyond the first person who receives it. Okay, so let's see if we can write this down in a more concise form. Notice we have each term has 1,000, and so we could easily factor that out. And so now we have 0.9 to the 1 plus 0.9 squared plus 0.9 cubed, and so on. And so you could write this as the sum of 1,000 times 0.9 raised to the n, and we want all of the powers of n from 1 to infinity. And notice this is again a geometric series. The ratio of consecutive terms is 0.9, and the constant term is 1,000. And here the sum started with 1, but if we wanted to, we could actually shift the index of this sum. We could write it as, well, let's start with n equals 0. And let's see, if we want the first term right, we should have a 1 power of 0.9. So we don't want to start with n here, because that would give us 0.9s. We want to start with n plus 1 for our exponent. And you'd see that that would give you exactly the same terms. N equals 0 gives us an exponent of 1. N equals 1 gives us an exponent of 2, and so on. So we'll actually get all of the same things that we had above. And we could even simplify that further and write it as n equals 0 to infinity. I'm going to pull off one factor of 0.9, and so we'll have 900, if I merge that together with a 1,000, times 0.9 to the n. And so you'll see we could just as easily think of this as a geometric series with c equals 900 and r equals 0.9, but starting with n equals 0 and starting with n equals 1. Okay, so all of these are different examples of real-world scenarios where geometric series might be used to describe what's going on. In the next video, we'll actually look at how we can start to figure out whether these series converge or not.